Makeup Exam 2-2 for Genetics 311 by Callie Cole. Okay, so in this prompt, we were either going to be making up or using a real organism to demonstrate one of the following population genetics forces. I went with inbreeding. And so the organism I used was a horse. The genetic trait we're looking at is coat color. The two alleles would be big B and little b. The three genotypes would be homozygous, big B, heterozygous, or homozygous, little b. And the three phenotypes would be black, gray, and white for the three respective genotypes. Inbreeding is when you mating of relatives that change frequency of genotype, but not the allele frequency. So that's the way we can double check at the end to make sure that our before and after numbers are correct. And then we can also look at the inbreeding coefficient, which measures the probability that two alleles are identical by descent. And the variable for that would be F, a capital F. F equals 0 means there's no inbreeding, and if F is between 0 and 1, that means there is some level of inbreeding occurring. And we can find F by using altered version of the genetic array that we use for the Hardy-Weinberg equation, which is right there. For reference, the Hardy-Weinberg, which is where we start, would have no mutations, no migrations, an infinitely large population, random mating, no selection, as in all the genotypes are fit for the environment. And so if you look at our before data, I just plugged in some numbers for our homozygous dominant. We had 25 individuals, heterozygous 50, homozygous recessive 25, so the total was 100. The allele frequency, so what you do to find the frequency of the big B allele would take all of this number and then half of the second, because there's one of each allele, and then divided by the total number of alleles. So that would be 25 plus half of 50 divided by 100, which gives you 0.5. That's also not only the big B frequency, that allele's frequency, but it would also be P as well. And then to get little b, you just subtract whatever you got for big B from 1, because they're always going to total up to 1. For genetic frequency, it would be the total number of each of the individual genotypes divided by 100 each. So for homozygous dominant is 0.25, heterozygous 0.5, and homozygous recessive 0.25. And then if we look at the after, it's pretty similar. Again, with inbreeding, the allele frequency shouldn't change because it's going to be the same genetics in the population, but the genotypic frequency would change. And then with inbreeding, that usually leans towards an increase in the homozygous genotypes. So we plugged in the numbers: 40 homozygous dominant, 40 homozygous recessive, and 20 heterozygous. The allele frequency, we find it the same way, but it should still be the same number at the end, and it is, it's 0.5. Genetic frequency, we find it the same way as well, and you get 0.4, 0.2, and 0.4 again. And then to find the breeding coefficient, we plug those P's and Q's, which again, this is the frequency of the big B would be P, frequency of the little b would be Q. Plug those into our altered genetic array, and we use just the first portion up here. With that, you can take the P squared plus F times P times Q and set it equal to the frequency of big B. And then when you do that, we find that the frequency of inbreeding coefficient is 0.6, which is appropriate. It should be greater than 0, but not greater than 1 in order to prove there was inbreeding occurring.